This resource is the sixth in a series on derivatives. We will explain the concept behind derivatives and formally define them. We will discover how to find the derivatives of various forms of functions, including polynomials and trigonometric functions. We will consider how to differentiate products, quotients, and composition of functions. We will also consider applications for derivatives and how they relate to real-world situations. We have discovered how to derive functions that are multiplied or divided by one another in previous resources. How do we find the derivative for the final method for combining functions, composition? Recall that the idea behind composition is to have functions acting as the inputs for other functions. To find the derivative for function composition, we must use the chain rule. Assume we have two differentiable functions, f of x and g of x. The function we want to differentiate, p of x, is equal to f of g of x. The chain rule says that the derivative p prime of x is equal to f prime of g of x multiplied by g prime of x. In other words, p prime will be the derivative of the outside function with the inside function as the input multiplied by the derivative of the inside function. Let's see an example that shows that the chain rule really does work. Suppose we want to find the derivative of the function p of x equal to the quantity x cubed plus 7x squared. We will first use the chain rule to find this derivative. Then, as a proof of concept, we will expand the polynomial and use the rule for finding the derivative of polynomials. To use the chain rule, we need to have a composition of functions. It helps to identify the outside and inside functions. We recognize that the outside function, f of x, is x squared. The inside function, g of x, is x cubed plus 7x. The derivative of the outside function, f prime, is 2x. The derivative of the inside function, g prime, is 3x squared plus 7. So the derivative of the entire function p of x will be 2 multiplied by the quantity x cubed plus 7x multiplied by the quantity 3x squared plus 7. If we multiply this out, we get a final form of 6x raised to the 5th power plus 56x cubed plus 98x. But what would we have gotten as the derivative if we expanded the function from the start? When we square x cubed plus 7x, we get p of x equal to x raised to the 6th power plus 14x to the 4th power plus 49x squared. Finding the derivative of this polynomial, we have 6x raised to the 5th power plus 56x cubed plus 98x. So either method gives us the same answer. So why do we need the chain rule? Not all functions compose as nicely as this first example, as we shall see. Suppose we have the function f of x equal to the natural logarithm of x raised to the 5th power. We have an outside function of x raised to the 5th power and an inside function of the natural logarithm of x. The derivative of x to the 5th is 5 multiplied by x to the 4th power. The derivative of the natural logarithm is 1 over x. F prime is therefore 5 multiplied by the natural logarithm of x raised to the 4th power multiplied by 1 over x. We can simplify this slightly to look like 5 multiplied by the natural logarithm of x raised to the 4th over x. But what if we have a function of a function of a function? In notation, we would have p of x equal to f of g of h of x. If we want to find the derivative for p of x, we need to start with the derivative of f of x and evaluate that for g of h of x. This is multiplied by the derivative of g of x evaluated for h of x. We finish by multiplying by the derivative for h of x. So we work our way inside the function, taking derivatives and linking them together as we go. Let's see an example. Suppose we want to find the derivative of the function f of x equal to the tangent of the natural logarithm of 4x squared minus 3x. F of x is the composition of three functions. The outermost function is tangent, the middle function is the natural logarithm, and the innermost function is the polynomial 4x squared minus 3x. Because we want to use the chain rule, we need to find the derivative for each of the components that make up f of x. The derivative for tangent of x is the secant squared of x. The derivative for the natural logarithm of x is 1 over x. The derivative for the polynomial is 8x minus 3. The overall derivative f prime of x is therefore the secant squared of the natural logarithm of the quantity 4x squared minus 3x multiplied by 1 over 4x squared minus 3x multiplied by 8x minus 3.